Now, good morning, friends. Last we discussed about the theory of chapter 10. We completed, and also we up to date to discuss the numerical of exercise 10.7. Now, today we are going to discuss the remaining numerical of exercise. Now, 10.9. First, we take the 10.9. Now, what is given? The light of wavelength 5000 angstrom is given, falls on a plane reflecting surface. What are the wavelength and frequency of this reflected light? And also, we have to find out for what angle of incidence if the reflected ray normal to the incident ray. Now listen, here the wavelength does not change during the phenomena of reflection. Only the frequency is changed. For that purpose, wavelength of reflected ray is 5000 angstrom, that is remains same, and frequency is F is equal to C upon lambda, because we know that the C is equal to F into lambda. Using this equation, we can find out the frequency of reflected ray. Therefore, F is equal to C, 3 into 10 raised to 8 upon 5000 angstrom. That means the 5000 into 10 raised to minus 10 meter. So, thus we obtain 6 into 10 raised to 14 meter. That is the second plus, therefore hertz. Frequency. Therefore, the frequency of reflected ray is 6 into 10 is to 14 hertz. Now we have to find out for which angle of incidence the reflected and incident ray are normal to each other. For that purpose, we consider the phenomena of reflection is that there is the surface, there is the normal one at the point of incidence. There is the incident ray, and reflected ray is normal to incident ray. So both has the angle is 90. So this angle is angle of incidence and this angle is angle of reflection R. I plus I is equal to 90. I plus I is equal to 90. There is reflected and that is the incident ray. Incident ray. Now here, what is given? Incident ray and reflected ray. Are normal to each other. Normal to each other. Therefore, I plus R is equal to pi by 2 for the 90. But we know that for laws of reflection, but I is equal to R, therefore 2I is equal to 90, therefore I is equal to 45. Thus, for 45 degree of angle of incidence, the reflected ray and incident ray are normal to each other. Again, friends, wavelength does not change during the phenomena of reflection and refraction, only the frequency is changed. Therefore, the wavelength of reflected ray is 5000 angstrom, same as the wavelength of incident ray. And frequency of reflected ray is, we can calculate by using this equation, C is equal to F lambda, therefore F is equal to C by lambda. C is the velocity of light in vacuum, 3 into 10 is to 8, and lambda is given 5000 angstrom, convert into meter. Therefore, frequency of reflected ray is 6 into 10 is to 14 hertz. Now, in statement, where the question what is given, incident ray and reflected ray are normal to each other. Therefore, from figure, I plus I is equal to 90. But law of reflection says that angle of incidence and angle of reflection are same. Therefore, I is equal to R. Therefore, 2I is equal to 90. Therefore, I is equal to 40. After that, next numerical, example number 10.10. The same numerical also given in illustration 10.7. What is the question of 10.10? Estimate the distance for which the ray of optics is good approximation for an aperture of 4 mm and wavelength 400 nanometer. Here, aperture is given, that is the A is equal to 4 millimeter. Convert into meter, 4 into 10 is 2 minus 3 meter. Wavelength used, lambda is 400 nanometer. Therefore, 400 into 10 is 2 minus 9 meter is equal to 4 into 10 is 2 minus 7 meter. Now, the final distance already discussed in theory portion. The limitation of the ray optics. For we derive the equation of the final distance. The final distance ZF is equal to S square upon lambda. A is the diameter of repulsion and lambda is the wavelength of the light used. Therefore, A is given. That means the 4 into 10 is 2 minus 3 1 square upon 4 into 10 is 2 minus 7. Therefore, 16 into 10 is 2 minus 6 upon 4 into 10 is 2 minus 7. 4 for the 16, therefore 4 into 10, that means the 14 meter. Now, the 40 meter distance, the good approximation of the ray optics is obtained. Right? For given aperture of a lens and also the wavelength 400 nanometer. Now in 10.7, here the 3 nanometer and 300 nanometer wavelength and 3 millimeter aperture is given. Okay, we discuss later when we discuss about the numerical of illustration. Now 10.8 of example or the exercise. There is also similar to the 10.9 illustration. Okay, what is the given the question? What is the Brewster's angle for a 2 glass transition? That means the unpolarized light is incident on the surface separating the A medium and glass. Unpolarized light is incident on the interface A to glass. There is the unpolarized light is incident. Here there is the plane polarized, and here there is the plane polarized, there is the polarized light. Like this way, figure is only for understanding. Here there is the unpolarized light. Here the plane polarized light is obtained, and here we obtain the polarized light. Here the angle of incidence, that is known as the angle of polarization theta p or the IB, Brewster's angle. Right? For that purpose, we assume that if the Brewster's angle is theta p. Therefore, from Brewster's law, is that tan theta p is equal to mu g a, glass air interference. Glass and air interference. Mu is equal to, or the effective index of the glass and air medium. So it's equal to mu z upon mu a is equal to tan theta p. But for a medium, for glass medium, the effective index is given mu z is equal to 1.5. For A medium, effective index is 1. Therefore, tan theta P is equal to 1.5 upon 1. That means the 1.5. Now, in natural tangent in log table, 1.5 is obtained for 56.19 degree angle. That means the 56 degree 19 minute. Approximately consider this the 57 angle degree. Therefore, tan 56 degree 19 minute is equal to 1.5003. Therefore, theta P is equal to 56 degree 19 minute, or there is the 57 degree. So that is the booster's angle for A to glass transition. So very easy numerical. Frequently this type of the numerical asked in competitive exam would set and also the NEET. Clear this? Okay, very short and sweet numericals. Again, in 10.10, estimate the distance for which the ray optics is good approximation for. Given aperture is 4 mm and wavelength is 400 nanometer. So aperture, wavelength we convert into meter. So 4 into 10 is to minus 3 meter aperture, and wavelength is 4 into 10 is to minus 7 meter. Okay. Now the final distance ZF is equal to S square upon lambda. We substitute the value 4 into 10 is to minus 3 whole square upon 4 into 10 is to minus 7. So we obtain 40 meter. Is the up to this distance the good approximation of the ray optics is obtained. Now next, what is the booster's angle for A to glass transition? The effective index of glass medium for the glass material is given 1.2. Here the figure is only for one knowledge. What is the booster's? Look, the tangent of the angle of incidence for which the incident ray becomes the perpendicular to the reflected ray is equal to the effective index of the medium. That is the statement of the booster's law. Therefore, tan theta P is equal to mu. Here, the effective index of glass with respect to the air, therefore mu ZA is equal to mu Z upon mu A. Now, effective index of the glass is given 1.5. For A medium, the effective index is 1. Therefore, tan theta P is equal to 1.5. Therefore, in natural tangent in log table, for 1.5 value is obtained for angle 56 degree 19 minute. Therefore, instead of the theta P, we take the 56 degree and 19 minute. So we obtain the value is 1.5003, and therefore theta P is equal to 56 degree 19 mean approximate the 57 degree. The same answer we obtained also in illustration 10.9. Clear this? Okay. So here the numerical of exercise are completed. Now we discuss about the remaining numerical of illustration. I think up to the 10.3 illustration we discussed it. Okay friends, after the completion of the numerical of exercise, here in illustration up to 10.3 we discuss. Now 10.4 is theoretical, we discuss in last. Now in 10.5 illustration, what is given? In example 10.3, Here we are using the data of example 10.3. Which data? Here the width of a slit is 1 millimeter and the distance between the slit and screen is 1 meter. These two data we are using. Therefore, we have written the D is equal to 1 millimeter and capital D is equal to 1 meter distance. 1 meter distance. Here width of a slit is, here we consider D dash 1 millimeter and the distance between the slit and screen is 1 meter. Okay. What should be width of each slit be to obtain the 10 maxima or the 10 bad fringes of double slit pattern? Double slit pattern, that means the stationary interference Young's experiment, and single slit pattern is the diffraction pattern. Okay. Within the central maxima of the single slit pattern. Now, question is quite hard not to be understand. For that purpose, first we simplify the question. In question, what is given? In Young's double slit experiment. Here width is given, that is the D dash is 1 millimeter is given. Distance between the slit and screen, that is the screen is given. This separation capital D is equal to 1 meter. At that time already we discussed in the Young's double slit experiment. Here the bad and dark fringes are obtained. Each fringe is of the same width. Here the central maxima is obtained. The width of the central maxima is this. All bad fringes of equal width in interference pattern. So there is the width of a central maxima and is equal to 2 lambda capital D upon small d dash. Clear or not? Okay. Now, we are using the single slit experiment. That means the diffraction pattern. In diffraction pattern, here the slit is like this way. Width of this slit is D. Instead of the two slits, we are using the single slit. That means the separation between the slit and screen is same. Here we need to find out this distance or the width of the slit. Within this width, already we obtain the width of a central maxima in interference pattern. In diffraction pattern, there are the 10 bad fringes are obtained. 10 bad fringes, that means the 5 bad fringes at below and 5 bad fringes above. That means the 10 bad fringes are obtained. Width are same on the scale. In that case, we have to find out what is the width of each slit. Again, here we have to compare the both experiment of Young's double slit experiment and the diffraction pattern. In Young's double slit experiment, we are using the two slits. Separated by the distance is given the 1 millimeter and the separation of the slit and screen is 1 meter. At that time, whatever the width of a central maxima. In this width, in diffraction pattern, we obtain the 10 bad fringes. 10 bad fringes. 5 above the central maxima, 5 below the central maxima. Clear this? So in that case, what should be the width of the slit? We have to find out. Therefore, we can add like this way for diffraction pattern. There is a single slit of width D. Width D. For diffraction pattern, there is a single slit of width, right? Okay. Suppose there is the D, there is the D. Okay. Width D. The width of central maximum is 2 lambda capital D upon small d. For stationary interference, there are 2 slits. There are 2 slits of width, 2 slits, separation of slits, suppose D dash, the width of 10 maxima is 10 lambda capital D upon D. But both widths are same. Therefore, 2 lambda upon D is equal to 10 lambda capital D upon D. That is cancelled. Therefore, D is equal to 2 D dash upon 10. That means the D dash upon 5. D dash is given 1 millimeter by 5. That means the 0.2 millimeter. This is the answer. The width of each slit is 0.2 millimeter. Again, the question is not easy to understand. Here we have to compare the both interference and diffraction pattern. Interference pattern, the 2 slits are obtained, 2 slits are using. At that time here the width of the central maxima. At that time here the 10 bad fringes are obtained for interference pattern. For diffraction pattern, the width of the slit is D. At that time the central maxima, width of the central maxima. Within this width, here we obtain the 10 bad fringes for stationary diffraction, stationary interference. So both widths are same. We compare this, so we can find out the width of a slit in diffraction pattern, that is of 0.2 millimeter. 0.2 millimeter. Clear this? So here figure is not necessary, figure is only for our understanding what this numerical suggests. After that, the next question is that, assume that the light of the wavelength 6000 angstrom is coming from the star, 6000 angstrom. We convert into centimeter. Why the centimeter conversion is required? Is coming from the star. What is the limit of resolution of telescope? Whose objective has the diameter of 10 inch? Diameter D is given the 100 inch. 1 inch is given as the 2.54 centimeter. Therefore, 100 into 2.54, that much centimeter. And due to here, the diameter is in centimeter, we convert the wavelength into centimeter. Therefore, 6000 into 10 is to minus 8 centimeter. What is the limit of resolution? Angular limit of resolution of the telescope. Angular limit of resolution of telescope is alpha minimum is equal to 1.22 lambda upon capital D. 1.22 lambda upon capital D. Here we substitute the value 1.22 lambda 6000 into 10 is to minus 8 upon 100 into 2.54. As we simplify it, we get the answer is 2.882 into 10 is to minus 7 radian, because alpha is the angle. Again, the angular limit of resolution of a telescope is alpha minimum is equal to 1.22 lambda upon D. We substitute the lambda as 6000 into 10 is to minus 8 and capital D 100 inch and 1 inch is equal to 2.54 centimeter. So we obtain the answer is this. There is the value of alpha minimum. Now, there is our answer, but sometimes they will also ask, what is the angular resolution power of telescope? Therefore, angular resolution power of a telescope is P is equal to 1 upon alpha minimum. 1 upon alpha minimum is equal to 1 upon 2.882 into 10 is to minus 7 into 10 is to minus 7. Therefore, we obtain 3.47 into 10 is to 6 radian inverse. That is the angular resolution power of telescope. Our answer is this, but this numerical is also extended like this way. Angular resolution power of telescope is this. Now after that, the next numerical is 10.7. Already we discussed this numerical is similar to our numerical of exercise. We find out the final distance. Here again in illustration 10.7, for what distance is ray optics has a good approximation when the aperture is 3 millimeter. Aperture size of the aperture is given, that is the 3 millimeter. Convert into meter, 3 into 10 is to minus 3 meter. Now, the wavelength is used 500 nanometer. Lambda is equal to 500 nanometer. That means the 5 into 10 is to minus 7 meter. Minus 7 meter. Therefore, the final distance ZF is equal to S square upon lambda. A is given 3 into 10 is to minus 3 whole square upon 5 into 10 is to minus 7. So is equal to 9 into 10 is to minus 6 upon 5 into 10 is to minus 7. Therefore, the final distance is 18 meter. Final distance is 18 meter. That is the answer. The same type of the numerical we calculate in exercise. Okay. After that, the 10.8. Also the same type of the numerical we discuss in exercise 10.9, I think. Okay. Unpolarized light is incident on a plain glass surface and reflected and reflected rays are perpendicular to each other. So, what is the Brewster's angle? What is the Brewster's angle? So here directly we have to obtain the tan theta p is equal to mu, because in Brewster's law the angle of incidence for which the reflected ray and reflected ray are perpendicular to each other, and we derive this equation from Brewster's law. Tan theta p is equal to mu. Here 1.5 for glass. Earlier the same numerical. For which angle we obtain the 1.5? 56 degree 19 minute approximate 57. Therefore, tan 56 degree 19 minute we obtain the 1.5003. Therefore, theta p is equal to 56 degree 19 minute approximate 57 degree. 57 degree. Here the question are given quite different, but here the calculation and answer is remain same. Calculation and answer is remain same. Therefore, the Brewster's angle is 57. Or for what angle of incidence the reflected ray and reflected ray are perpendicular to each other, for this angle 57 degree angle, and that is known as the Brewster's angle, or the angle of polarization. Clear this?